Okay, welcome back to the today's class. Today we will be seeing about star and delta connection, transformations and problems related to star and delta connection. Three-phase supply connections. In a single-phase system, two-wire is sufficient for transmitting voltage to the load. Okay, in nowadays we are using alternating current for our home appliances to be powered up. So when you consider or connecting home appliances, there will be two wires. One is phase and another one is neutral. Okay, so these two wires are enough to power the supply to your home appliances. In case of three-phase systems, two ends of each phase R1, R2, Y1, Y2, B1, B2 are available. So, in a three-phase system, there are three coils. Okay, these three coils are known as phases. In these three coils, if you take this coil, you have two ends. Okay, these two ends are named as R1 and R2. Similarly, on taking this coil, you will be having two ends which is named as Y1 and Y2. Similarly, there is other two ends which is known as B1 and B2. So, this type of system is known as a three-phase system. Okay, so in a three-phase system is used to power a higher rating appliances such as a big motor or a air conditioning system which is used in your homes or factories, etc. If all the six terminals are used, then six wires are needed to transfer power. So if you connect all these 6 points, that is R1, R2, Y1, Y2, B1 and B2 towards the load, then you need six wires to connect the load. Okay, so to minimize the wires, that is to make the transmission of power from one end to the other end in a very cheaper manner. What becomes cheaper? Okay, if you connect six wires, then the six wires should be of metal. Similarly, we will be using aluminum and copper as a metal for transmitting the alternating current from your remote substation to your home. Okay, so if you use a metal like this, then the metal cost is high. Okay, if you use a copper wire to transmit electricity from your substation, which is near to your home, to the transformer, which is present very near to your home, then it will say up to it may have 5 kilometers or 6 kilometers. So up to 6 kilometers, you draw a copper wire, then the length of the wire and the material used makes a heavy cost. Okay, if you need six such wires, then the cost of a single wire, take it is 1000 rupees, then the six wires will have 6000 rupees. Oh, so it becomes very costly. I am saying for example, but it will not be 1000, it will be in lakhs. Okay, so it will be in 6 lakhs or 60 lakhs, such rupees may occur. So to minimize the use of the phase voltages to be come to the home, we need to minimize the amount of wires which we are drawing from the substation to our homes. To reduce the cost, the three phases are interconnected to form two different combinations. So, if you take an alternator which is delivering power in the generating station, here the generating station represents a thermal power station or a nuclear power plant or a tidal power plant or a windmill. Everything has an alternator present in it. Okay, this alternator which is present will produces three-phase electricity, that is the alternating current. Okay, the three phases of the alternator are here, which is R1, R2, Y1, Y2 and B1 and B2. So don't worry about the alternators and how the alternators produce current. It is not now needed. Okay, we will see these things in the second and third unit. Okay, now you need to know alternators are producing current which are converting mechanical energy to electrical energy, and inside the alternator we are having three windings R1, R2, Y1, Y2, B1 and B2. Okay, these windings are connected. If they are connected out, they will have six wires like this, and if we transmit these six wires from the generating station to our home, it will be very costly. So to avoid these things, we are using three-phase supply. So how a three-phase supply is formed is by interconnecting these R1, R2, Y1, Y2 and B1 and B2 into two different combinations. So while connecting these 6 wires in two different combinations, we have two things that is known as star connection and another one is delta connection. Okay, these 6 wires can be interconnected in the form of a star as well as delta. So today we will be seeing how a star connection is performing and what are its equations. Similarly, how a delta connection is made and what are all its equations related to the voltage and current parameters. Star connection. The star connection is formed by connecting, starting or terminating end of all the three windings together. See, this one is the star connection. You seen in the previous figure R1, R2, Y1, Y2, B1, B2 are the three phases and these three phases are connected together. That is the last end R2, B2, Y2 are connected together to form one single point. Similarly, the other free ends which are R1, B1, Y1 are taken out and the three-phase supply is formed. This RYB is known as the three-phase supply which is delivered from an alternator. This three-phase supply is available in the generating station as well as in the transmission line as well as in your home. Okay. The ends of R1, Y1, B1 and are connected with the ends of R2, Y2, B2 together. Okay, that means the three phases are connected. That is, the phase to phases are connected in such a manner that here R2, Y2, B2 are connected together, whereas R1, Y1, B1 are taken out. Okay. The common point is called as a neutral and represented as N. This is the common point where R2, B2, Y2 is connected and this point is known as the neutral point. The remaining three ends are brought out for connection purpose. So the remaining three ends represents R1, B1 and Y1 which are brought out which is used to connect it to the load. That is nothing but your house appliances or a air conditioner or any other device which are used by you. These ends are referred to as R, Y and B. So this connection can be alternately drawn like this. Okay, you see R1, Y1, B1 is here and from these things the three connections R, Y, B is present and this is connected to the load, whereas R2, Y2, B2 is connected together and formed a neutral connection. Okay, these two connections are same and similar. Once you redraw this connection like this, then you will get this circuit. Okay, delta connection. The star connection is formed by connecting one end of winding with other end. Connections are continued to form a closed loop. Here in the delta connection, what you are doing is you are connecting the two terminals of the phases, that is R1 and B2 is connected. Similarly, B1 and Y2 is connected. Y1 and R2 is connected. So all the two phases, each end of the phase is connected with each other. So while doing so, a closed path is formed and this closed path gives you a delta connection. So at the end of these three closed paths, you can get RYB which is connected to the load. So this connection is known as delta connection. The supply terminals are taken out from the three junction points. That is nothing but this is the junction point, this is another one and this is another one. So the terminals are taken out. Three terminals are there. So three terminals are taken out from the three junction points. There is no common point or neutral. Okay, here in the delta connected system there is no neutral, whereas in a star connection there is a neutral as is seen in the earlier slide. Okay, the circuit diagram is shown in the below figure. Oh, this is the circuit diagram. Okay, and then connecting, redrawing this circuit, you will get R, Y and B similar to the same connection. You can see R1, R2, Y1, Y2, B1 and B2. You see R1 and B2 is connected. So what you need to do is connect R1 with B2. Okay, and take out R over here. Then you see here R2 and Y1 is connected. So what you need to do is connect R2 with Y1 and take out Y over here. Next you see B1 and Y2 is connected. So connect B1 and Y2 over here and take out the line B over here. Okay, these three lines will be connected to your load. Okay, concept of line voltage and line current. The potential difference between any two line of supply is called the line voltage. Okay, you know voltage is nothing but the potential difference. Okay, here the line voltage is known as the potential difference between two lines. The current passing through the line is known as line current. Okay, if the current is flowing through the line, then it is known as line current. Okay, for a star connected system, consider this one is the star connected system. In star connected system, the line voltages are denoted by VL. Okay, these are represented by VRY, VYB, VBR, and line currents are denoted by IL. These are IR, IY, IB, and is shown in the figure. So this is the star connected system. Here the neutral point is present over here, and here is the R1, B1 and Y1, from which we are having the R terminal, Y terminal and the B terminal. Here the R represents the color ranges. Okay, R is red, Y is yellow and B is blue. Okay, if you measure the potential difference, that is the potential difference between any two lines of the supply is called the line voltage. So if you measure the potential difference between VR and VY, then it is known as VRY. The difference in potential between R and Y is known as VRY. Okay. Similarly, the potential difference between Y and B is known as VYB. And similarly, the potential difference between R and B is known as VBR or VRB. No change is present. Okay, if you put VBR, which will be equivalent to VRB. Okay, it is not a problem. Okay. And similarly, if you see the line currents IL, these are denoted by IR, IY and IB. So the current flowing through the R line, this line, is known as IR, whereas the current flowing through the Y line is known as IY, whereas the current flowing through the B line, that is the blue line, is IB. Okay, these are connected to the load as it is. Okay. Then, in delta connected systems, the line voltage are denoted by VL and these are represented as VRY, VYB, VBR. And the line currents are denoted by IL. These are IR, IY, IB, and it is shown in the figure. Okay. Okay. Now the figure is clear. Here is the delta connection, and you can see the ends R1, B2, B1, Y2, Y1, R2 are connected, and the three ends. These three ends are taken out to form R, and this end is taken out to form Y, and this end is taken out to form B. Similarly to the star connection, the line voltages are represented as the voltage, that is the potential difference between R and Y is VRY, and the potential difference between Y and B is nothing but VYB, and the potential difference between B and R is nothing but VBR. Okay, similarly the line currents are represented as IR, IY and IB. Okay, these are the three line currents and the three potential differences for delta connected system. Concept of phase voltage and line current. Phase voltage and phase currents can be seen by connecting three phase loads to supply lines. The load can be connected in three ways in a system. It may be connected in star or delta. Okay, in the previous two cases, you have seen the star connected system and a delta connected system. Okay, in these things, if the load is connected, what will happen? We are going to see this thing in phase voltage and line current in the concept of when load is connected. Okay. See, the concept of phase voltage and a line current, which is star connected load is present. Here, this is the supply points where R, Y and B are present. Okay. Here, from the terminals R, Y and B, you are connecting a load. This is the load. These boxes Z phase 1, Z phase 2 and Z phase 3. These three boxes are known as load. Okay, inside these boxes the resistance is present. Okay, a huge resistance is present inside these boxes. Now you see the three different impedances Z1, Z2 and Z3 are connected in star with the supply terminals R, Y and B. So these are the three impedances Z phase 1, Z phase 2 and Z phase 3. Okay, these three impedances are connected in star. See, this point is earthed. This is nothing but the neutral point, and the other three ends of Z phase 1, Z phase 2 and Z phase 3 are taken out, and Z phase R is connected to R, where Z phase B which is coming is connected to B, and Z phase Y is connected back to the terminal Y. Okay, so on seeing these things, you can see the line current is represented as IL, and the current IR is flowing through the R terminal, and the current IB is flowing through the B terminal, and the current IY is flowing through the Y terminal. So the phase voltages V phase across the branches of the three phase loads are known as VRN, VYN and VBN. Okay, you see this is the phase voltage, which is nothing but R to neutral. Okay, when you put a voltmeter across the terminals R and neutral, you will get the phase voltage VRN. Whereas if you put the voltmeter across the terminal Vy, that is the Y point, and the neutral point, you get the voltage Vyn. Whereas here, if you put the voltmeter across B point and the neutral point, you will get a phase voltage of VBN. Okay. Whereas in this star connected load, the current will be the same. That is, the phase current will be equivalent to the line current. IL will be equal to I phase. The phase current I phase through the branches of the three phase loads are IR, IY and IB. The line current IL through the branches of the three phase loads will be equivalent to I phase. So you know that since the line current are equivalent to phase current, the line current IL will be equivalent to the phase current IB. Okay, it is written in sentence. The suffix n is indicated for phase voltage in the star connected load because you are measuring the phase voltage irrespective of neutral point. So you see here VRN. Here the N represents the neutral point. VYN. Here N represents the neutral point. VBN. Here N represents the neutral point. So in a star connected load, the N is indicated in phase voltage. So if you measure a voltage in phase to phase, then the neutral point is there. Okay, that is VRN, VYN and VBN. The voltmeter should be connected from R terminal to the neutral terminal to measure the phase voltage of VR, that is VRN, and similarly for the other three phases also. Okay, the formulas present in seeing the phase voltage for a star connected load is V phase will be equivalent to VR equivalent to Vy, which will equivalent to Vb, and I phase will be equivalent to IR, which will be equivalent to IY, and which will be equivalent to IB. So the three currents are equal. So you get I phase current will be equivalent to line current. That is, the phase current which is flowing will be equivalent to the line currents also. Concept of phase voltage and line current in delta connected load. In the previous you have seen about star connected load. Now you are going to see about delta connected load. Three different impedances Z1, Z2 and Z3 are connected in delta with the supply terminals R, Y and B. So this is the supply terminal R, Y and B. So from these supply terminals, three lines are taken out and these three lines are connected in delta. How it is delta is, you know that the Z phases has heavy resistances present in them. So these three resistances are connected end to end to form a closed path. Okay, if these resistances are connected end to end, you will get a closed path like triangle. Okay, so these three ends of the triangle are connected to R, Y, and B. The phase voltage V phase across the various branches of the three-phase load are VRY, VYB, and VBR, whereas the phase currents are IRB, IYB, and IBR. The line currents through the branches will be equivalent to IR, IY, and IB. So the difference between the star connected and the delta connected is close. Partially you can see in the star connected load the line current will be equivalent to phase current, whereas in delta connected load the line voltage will be equivalent to phase voltage, and the line current and the phase current are different. If you see the phase current, you will get IRB, IYB, and IBR. Okay, whereas in the line current you will get IR, IY, and IB. What I am saying is, if you see the line current here, this will be IR. Here it will be IY, and here it will be IB. When you see the current which is flowing in this line, you will get IBR. Here, through this line, you will get IRY, whereas through this line, you will get IYB. So, the phase current and the line currents are different. The formulas used are V phase is equivalent to VRY equal to VYB equal to VBR. We know the line voltage will be equivalent to phase voltage in delta connected loads, whereas the phase currents are represented as IRY, IYB, and IBR, whereas the line currents are represented as IR, IY, and IB. Relations for balanced star connected loads. Consider a balanced star connected load. You will get the following formulas, which is nothing but the line voltage, which is VL, will be equivalent to VRY, which will be equivalent to VYB, and which will be equivalent to VBR. Whereas the line currents, which will be equivalent to IL equal to IR equal to IY, which is equivalent to IB, not a minus, it is also equivalent. Okay. And phase voltage, V phase is equivalent to VY, VR, VY, and VB. Whereas the phase currents, I phase will be equivalent to IR equal to IY equal to IB. For star connection, the line current will be equivalent to phase current. For line voltage, you can see the VL, that is the line voltage, will be equivalent to √3 times the V phase. So, to find the line voltage in a star connected load, what you need to do is multiply √3 in the phase loads, V phase, multiply √3 with V phase. Okay. In a single phase power, if you measure power for a single phase system, then what you need to do is multiply V phase, I phase into cos pi. Here cos pi is represented as power factor. You will see power factor in the next unit. Okay. V phase, I phase, and cos pi should be multiplied to find the single phase power. Three phase power. To find the three phase power, what you need to do is just multiply √3 to the single phase power. Okay. Which is nothing but √3 into VL, IL, cos pi. Here, you need to see the difference. Here, for a single phase power, you need to take the phase voltage and the phase current. Whereas in the three phase power, you need to take the line voltage and line current. For star and delta connected loads, the phase voltage and line currents will vary. So, you need to use the line currents for three phase powers and line voltages for three phase powers while calculating using these formulas. The phase impedance, this phase impedance nothing but Ohm's law. Here resistance, Z represents resistance. Okay, Z phase will be equivalent to V phase divided by I phase, which is nothing but R is equal to V by I, nothing but Ohm's law. Because it is an alternating current, you are mentioning it in AC supply, you are getting modulus of Z phase, which will be equivalent to modulus of V phase divided by modulus of I phase. Star to delta transformation. I ask you to write down this formula in your notebook. This is the star connected load. If you need to convert a star connected load into a delta connected load, please copy this slide into your notebook. Okay. This is the R connection and this is the neutral point. Here is another Y and here is B. Sorry, it is represented as R. It is nothing but B. Okay. RYB, this thing is converted into star connected load. Okay, to do this thing, what you need to use is this formula. Here, in this given, they will give you this thing. Okay, they will give you values. You need to convert these values into delta. To do this, what you need to do is for RA, to find RA will be equivalent to R1, R2 plus R2, R3 plus R3, R1 divided by R1 is the formula. Okay. You just note this thing as it is in your notebook. Complete பண்ணியாச்சா?
Completed, sir.
பண்ணிட்டீங்களா?
Yes, sir.
Okay. For delta to star transformation, draw this thing. Okay. After completing it, please tell. You can see this is the delta connected load. Here all the three ends are connected. Okay, everything is connected. Okay, this terminal is connected with this terminal and this terminal is connected with this terminal and this terminal is connected with this terminal. So you will get a triangle and the three ends of the triangle are known as R, B and Y. So this triangle looks like a delta, so it is named as a delta connection. Whereas in the previous case, the connection looks like a star. Okay, if it is looks like a star, they have named it as star connection. Okay, that's all the difference in name. With their appearance, they have given the name. That's all. Here we are. What we are doing is converting the delta into star. All the values for delta will be given. Then you need to convert the delta into star. To do this, you need to use this formula. Okay, nothing but R1 will be equivalent to RBC divided by RA plus RB plus RC. Okay, that's all is the formula. Use this formula, then you will get the star connection. That is the R1 value for the delta. Okay, what we are doing here is very easy step is to convert deltas to star. You see the common things here. The denominator is RA plus RB plus RC, and for R2 also the same thing is present. For R3 also you see the same thing is present. Okay, the only difference is the numerator. To find R1, to find R1, what you are doing is multiplying RB and RC. Okay, join these two things. Okay, to find this link, what you need to do is multiply RB and RC. Okay, for R2 over here, to find this thing, what you need to do is multiply these two things, RA and RC. See, to find R2, you are having RA and RC multiplied. Whereas to get R3, what you are doing here is multiply these two things, RA and RB divided by RA plus RB plus RC. Okay, this denominator is common for all the three connections or all the three formulas. What you do is just multiplying the resistance, which is very equivalent to it. If you need to find these things, that is this one. If you need to find this one, what you need to do is multiply these 2 points. If you need to find this point, what you need to do is multiply RA and RC. Okay, if you need to find this top one, what you need to do is multiply this RA and RB. That's all, very easy. You can get the formulas. Okay, completed. Mitrashri, do you complete that?
Yes, sir.
Okay. Okay, this is the problem. Now I ask you to write this problem over here. Okay, draw the circuit. Draw this star connected circuit. This one, and then draw this circuit as it is. Now use the formula that you have written in your notebook to convert star into delta. Okay, due to time constraint, I will show you the answer. Okay, this is the formula. Okay, to find RA, the formula is R1 R2 plus R2 R3 plus R3 R1 divided by R1. Okay, this is the formula. Okay, what you need to do is substitute the R1 R2 value. Here is R1, which is 8 ohm, and R2 value is nothing but 7 ohm. Put the plus over here. Next R2 R3. R2 value is 7 ohm, R3 value is 4 ohm, plus R3 R1. R3 value is 4 ohm and R1 value is 8 ohm. Put as it is, divided by R1, which is nothing but 8 ohms. Use a calculator to calculate the value. You will get 14.5 ohms. So put this value RA, that is the RA value here. The RA value is 14.5 ohms. So use the formula to calculate all the values. Okay, that's all very easy. This connection is B. Okay, don't put it as R. This connection is B. Okay, change it. Okay, this connection is B. I repeat, this thing is B. This is R, Y, and this one is B. Okay, I will move to the next problem. You just write the question. Yeah, I don't copy these answers. Okay, just write the question. Do it yourself. Okay. Next, for delta to star transformation, what you need to do is RB is 10 ohm, RA is 40 ohm, and RC is 5 ohms. Okay, so you can use the formulas to convert the delta connection into star connection. What you need to do is write the formulas for R1, RB, RC divided by RA plus RB plus RC. Substitute the values. RB is 10 ohm, RC is 5 ohm, that is 10 into 5, divided by RA plus RB plus RC, which is nothing but 40 plus 20 plus 5, which will give you 50 divided by 55, which will give you a value of 0.9091 ohms, which is R1 value. So the resistance R1 value is 0.9091 ohms. Similarly, you can find all the two values of R2 and R3 by using this formula. Calculate it. Thank you.